In this video we are going to look at the Unity Profiler. Profiler is for creators who want to enhance their projects by implementing optimization techniques to improve gameplay performance. It is generally recommended to set a target frame rate for your gameplay for benchmarking against during development. Depending on the specific cases, this may be 60 frames per second for desktops or 30 frames per second for mobile. Profiler will then allow you to evaluate your gameplay performance to ensure it is meeting your target frame rates. Profiling should be done at regular intervals through the entire game production process. If you want to follow along with this video, you can create a new project in the Unity Hub and download the URP 3D Samples Scene template. It features environments to help you learn how to use URP optimally across all platforms. It has 4 environments, each with different art styles, rendering paths, and scene complexity to represent the variety of 3D projects built with URP. A quick way to check gameplay performance is to use the Stats option in the Game view. This will display current FPS. Now this game is very well optimized, giving high frame rates on the desktop computer. To understand what is happening each frame, we can look at the order of execution for event functions on the Unity documentation. Here is the game loop that happens every frame and comprises physics, input events, game logic, scene rendering, GUI rendering, and end of frame. These are shared between the computer's CPU and graphics card's GPU, which must work together to render the frame. For a target frame rate of 60 frames per second, it must render every frame at 16.66 milliseconds or less. And for 30 frames per second, it must render every frame at 33.33 milliseconds or less. The CPU handles the Unity engine code and your own code as part of game logic. The render commands are passed down to the graphics card GPU to render the frame. Some frames may struggle to render at less than 16.66 milliseconds. The CPU may take longer to run the game logic code, creating a CPU-bound bottleneck. The graphics card has to wait until it receives the render instructions from the CPU. A GPU-bound bottleneck happens when the GPU takes too long to render the previous frame, forcing the CPU to wait until the GPU is ready to render this frame. We can now open the Profiler from Window, Analysis and Profiler. The Profiler is ready to record, so as soon as I begin playing, it will now begin recording frame by frame data. This is all CPU data. At any point, I can click in CPU usage to pause the game and analyze this frame. We can see that these frames are running higher than 5 milliseconds but less than 10 milliseconds, which puts it somewhere between 100 to 200 frames per second. This game is currently not maximized. This can make the game look more performant than it really is. Where possible, profiling should be done at the desired resolution the game is meant to be played at. If you intend for multiple resolutions, then it is better to profile each resolution in turn. CPU data is a combined view of all these categories, which are color mapped to the colors in the timeline view. We are profiling inside of the Unity editor, so the running of the editor is combined with the running of the game. The others category contains the Unity editor data alongside other things. It is much better to profile from an exported game which doesn't contain the Unity editor data and gives more accurate results. We will cover that a bit later. Any of these categories can be viewed in isolation to analyze individual performance. I will maximize this to see this better. There are numerous modules running such as rendering, memory, audio, video, etc. These can be switched on or off as needed. Click on a spike to analyze the results. The timeline section is going to give us an in-depth look at what is happening during that frame. Click here and press the A key to frame all. This frame took just 9.73 milliseconds to complete, from 0 to 9.73. This is showing us horizontally the timing of each CPU thread in this frame. The main thread is the CPU data, and the render thread is the render commands to be sent to the GPU. The CPU data and render threads are both taking place on the CPU. The CPU data thread is handling the game logic and the render commands. We can see here the game logic code and the render commands, which are passed over to the render thread, ready to pass on to the GPU to render the frame. We also have this editor profile marker because we are profiling inside of Unity. We can click on the profile marker and press F to frame it. This is the update script run behavior update, and it took 0.26 milliseconds to complete. If a CPU thread was taking too long, we could identify it here and work on fixing it. The CPU is also handing some data down into the jobs section. This makes use of the processor cores and multi-core threading to speed up CPU processing. Each worker corresponds to a separate worker thread that is responsible for running jobs concurrently. The number of workers you see depends on the number of available CPU cores on your machine and Unity's threading settings. It can give insights how effectively Unity is utilizing multiple threads to parallelize the execution of jobs. This can lead to improved performance on multi-core systems. We can click on the profile marker and choose to show in hierarchy. This moves us over to the table-based hierarchy where it presents each process in the parent-child structure. This process took 34.5% of the entire frame time to complete. We can also choose to view any of the available threads, such as render thread, to analyze more data. The table data can then be sorted based on highest and lowest values, making it easy to identify which CPU threads are taking the most time to complete. We can use the drop-down to jump back to the timeline. Right-click on the Profiler tab to enable colorblind mode if you are finding it hard to see the data. VSync is used to prevent screen tearing. Here is an example of screen tearing. The top part of the frame has not finished processing. The graphics card renders the part it currently has and uses data from the previous frame to render the missing part at the bottom, creating this visible tear between the two frames. VSync forces the graphics card to wait until it has complete frame data before rendering a frame. Screen tearing is then eliminated. VSync is enforced on mobile devices, but on desktop computers, it is an option that can be switched on or off. If I enable VSync, we are going to get very different data to what we saw previously. I will clear this data and begin playing again. We can now see the frame rate is capped at 60 frames per second. VSync is forcing the CPU to take the full 16.66 milliseconds to process data, preventing screen tearing. In the timeline, we can see an extended editor loop profile marker. This is forcing the CPU to take the full 16.66 milliseconds before processing the next frame. Now this is an example of a well-optimized game, but let's look at an example that has no optimization. This example scene is designed to put a lot of stress on the CPU and GPU. Each of these cubes have several real-time lights with shadows. Now adding more real-time lights in the scene puts more stress on the GPU. There are spawn points that spawn in spheres that have rigid body physics. In the script we can see the spawning happens every frame, but within that is a for loop that spawns 10 spheres per spawn point per frame. This will put a lot of stress on the CPU. The spheres are destroyed after 4 seconds, and I have a debug.log in a rotate script that returns a string reference every frame. Now this will put extra stress on the CPU. We now want to profile this externally, which gives the most accurate results. In the build settings, ensure this scene is in the build. The development build should be checked on and Auto Connect Profiler also checked on. In the player settings I have set this to a player window of 1280 by 720 and running background is unchecked. Now I can build the game. With the profiler open in Unity I can now run the external build. And we can see some spikes pushing the frame rate below 30 frames per second. Let it run for a few seconds and click to pause on a certain frame. Now generally most of it is running just above 30 frames per second, however these spikes are causing a frame dip. This frame took 80.66 milliseconds to complete. This first section is internal Unity scripts and physics, and this part is my scripts. And these are the render commands which are passed down to the render thread and then onto the GPU. My scripts are taking up the largest part of the frame, but the physics in orange are also taking up a big part of the frame. Physics run at a fixed update that will be much slower than the update. Because I am spawning in a large amount of spheres every frame with rigid body physics, the physics has to run to catch up with the update, causing some frames to have these large spikes as it runs larger amounts of physics updates. The render thread is having to wait 70.33 milliseconds before it can render the frame. This is a CPU bound bottleneck. This rotate update is taking 48.55 milliseconds. Let's see this in the hierarchy. And we can see this is all because of that debug.log. The physics is taking roughly a quarter of the entire frame. We can now see where the issues are and what needs to be fixed. First, I have ensured there is only one light per cube in the scene. On the rotate script I have commented out the debug.log. Now these are useful when developing your game, but remember to comment these out before profiling and remove them when building the final game. In the spawn script I have now changed the update to a custom function that is run by an invoke repeating every 2 seconds, putting less stress on the CPU and reducing the physics calculations required by the fixed update. This will reduce those large spikes we saw earlier. This is now staying at about 60 frames per second, so a good improvement. Leave it for a few seconds of gameplay and click to analyze a frame. Press A to frame all. This frame took just 16.61 milliseconds and is using VSync, seen here in yellow, to keep a constant 60 frames per second to reduce screen tearing. Now the scripting is taking up this small section. The rendering is here and this large section is waiting until it meets the target frames per second, which is 60. The CPU is idle for most of each frame, reducing the stress on CPU. Click on Physics and press F to frame it. This is now just taking 0.39 milliseconds. Let's look at the scripts. All of these scripts are completing very quickly because we commented out the debug.log. In the hierarchy we can see the scripts just took 0.1% of the frame time, and the physics is now just taking 3.1% of the frame time, so that's a big improvement from the quarter of the frame from before. This is an example of how we can optimize to improve gameplay performance. Saving data as a benchmark is important when profiling. You want a before and after comparison to ensure the changes you are making are improving gameplay performance. You can also present data in meetings to update your team on your progress. You can save the profiler data using the save icon and load it using the load icon. For accurate profiling when building mobile games, you will want to profile from the mobile device itself. Click here to find your connected device. The documentation explains how to set this up and link to a mobile directly or by using an IP address. To help during profiling, it is useful to follow along with this flowchart. You can easily identify if you have a CPU-bound or GPU-bound bottleneck by following the flow arrows. From there, it then gives tips on what could be done to fix the issues and improve performance. You will find this flow diagram in the profiling ebook found in the video description below. And that brings us to the end of this video. We have looked at how to use the profiler window both on internal games and external builds. We have an understanding of what is happening in the CPU usage window, in the timeline and the hierarchy sub-windows, and how to identify issues and fix them. Download the ebook below to find out more. Thanks for watching.